So I don't present a solution today, I rather present you a problem where we need your help to solve this problem. And it's the short-reach optical communication task, a real-world task for neuromorphic hardware. So neuromorphic hardware is always driven by benchmarks, as we've already seen today. So yin-yang data set or the NMNIST data set. And we have a lack, first of all, of real-world application, then of intrinsic temporal structure of the data sets, or they just require topologies that are really, really big. So it's hard to map it on chips and really apply it and bring it into industry. So what we want to propose today is just the optical data transmission task for small-scale SNNs. Talking about small-scale SNNs, we talk about 30 to 40 hidden layer neuron, one hidden layer. So that's what we and people from Heidelberg, with whom that paper is published together, already investigated, and we already proposed some solutions that were well received in the communication community. And what are the advantages? First, it's a real-world task, so the communication community is really interested in it. We have temporal data because it's a communication problem. I'm talking to you for the next 10 minutes, so we have that intrinsic temporal domain, and we have models of the optical fiber, which are pretty well suited to the real world, so we can generate data, and therefore we have unlimited data. And by the network operators, we have predefined communication system requirements, so they tell us, okay, you have to perform that good, otherwise there's no need to build it into a transceiver. And I guess it's interesting for the evaluation of the resource efficiency of your model, chip, or your hardware, prototyping the algorithms we've seen today, so you can compare with each other, and you can develop small-scale hardware with an actual application in mind. So what is the short-reach communication task? So we take a look at the IMDD link. That's a non-coherent communication task. We always have 2 bits, either 0 or 1, so grouped together. So we have 4 possibilities, and they are mapped to transmit symbol, and each level over here denotes 1 transmit symbol. So each level denotes a group of bits, and that's what our transmitter is doing, where we just have a laser, and the light of the laser is just modulated, so that's why it's called intensity modulation. We modulate the power of the laser, and then we couple the transmit signal onto optical fiber, and the receiver, we have a photodiode, where we have a direct detection via the photodiode, and then we have some thermal noise at the receiver, and then we receive YK, so that's what we observe at our receiver, and then we have a receiver. So what's happening in the channel? As you can already see, our transmit data is pretty clear, but the receive data, there's already some distortion, so that's not clear at all. And if we take a look at the distribution at the output of the channel, we have the histograms colored, independence of the transmit symbols, and you see there are some overlaps. So that's the communication engineering problem, how to decide if you have such overlaps. And the answer is you always make some errors. Our goal is to make the error as small as possible. And that's why we need to implement receivers that first eliminate impairments. So that's called equalization. And then estimate the transmit bits. That's called demapping. And the link impairments we have in the IMDD channel are first chromatic dispersion in the optical fiber. So you just send your short pulse, and then the fiber it broadens over distance. And then, of course, if it broadens, the neighboring symbols are affected too. We have the nonlinear detection of the photodiode, which equals to squaring. So that's the nonlinear operation. And as always, we have some additive white Gaussian noise. So that's the standard disturbance we have in communication engineering, which is due to amplifier noise. So the IMDD task we can model by this small equation. So it's a really simple model. The kth received sample, YK, we can model based on the kth transmit symbol and the n-taps neighboring symbol. So we have the smearing in time. And that means all the neighboring symbols somehow contribute to our received sample. And then we have an arbitrary function f, which is just a linear combination of all those transmit symbols, and also the nonlinear distortion. And we have the AWGN, which we just add. And Our task now is to find a receiver, which we just say is a function g now, which inverts the function f. So we just have our kth received samples. We can take the neighboring samples because we know, okay, there's the smearing of the neighboring transmit symbols. And then we somehow find a function which returns to us the bits we want to have. So we have two objectives. First, the communication engineering objective. We need to find a function g which minimizes the bit error ratio. So the number of bits that are wrong should be minimal. And the second one, it should be energy efficient. So no communication operator wants to build a receiver which consumes 100 watts of energy. It should be small scale, it should be energy efficient, so it will fit into your pocket or into your server rack. And that's why we provide the data set over here. So here's a GitHub link. And what we provide is just an IMDD link. So we sample random bits. Then you get the symbol labels ranging from 0 to 3, so 4 classes. It gets distorted by the IMDD link. You get the received symbols, so that's a vector y over time. And we already prepare it for you in chunks, as we discussed in the slide before, that you can directly process it. That will be your task, designing a receiver and obtaining the received data that perfectly fits to the transmit data. And we provide you two parameter sets, which we already introduced to the communication community, and I said was well received. So the first one we call the low chromatic dispersion set. I highlighted the most important parameters in red. So the first set has a dispersion parameter of -5, so rather small. So you only need 7 taps, so dispersion is weak, and you don't need that large SNN. And the second is the standard single mode fiber task. So it has a dispersion parameter of -17, so rather high, and you need more taps. Okay, the question may rise, why do we use that one if we have that one? If you transmit at a wavelength of 1550 nanometers, you have less attenuation. So that's what is used and standardized by the optical network companies. And we just provide both, so you can try out both. So we then also provide two solutions. So for each data set, we provide a solution. Keep in mind, we have two objectives. We want to minimize the BR, so that's the communication objective, and the second, minimize the energy efficiency. That's in that case the spike rate, because we have implemented our SNN-based receivers using NORs, and that's what I just said. Okay, spike rate is somehow scaled with the energy efficiency, and now we can take a look at the results. So on the left-hand side, you see 3 figures, which shows the BR plots. Independence of the noise power which disturbs, number of the hidden neurons, and the number of taps we're using for equalization. And if you achieve a curve which is below the yellow curve, you found a better solution which is more interesting for the communication people. And on the right-hand side, you see the number of spikes, which for the input and hidden layer which are created. And again, independence of the 3 parameters. And of course, here the same. If you're below the lines we provide, you found a better solution than we already have. And we supply a solution for the standard single mode fiber task too. So the papers from Heidelberg and Karlsruhe were just merged together, and then you just can compare to our solution, which we already introduced to our community. Okay, so what's our contribution today? So we provided an IMDD data set to you that you can really easily use to benchmark your neuromorphic hardware or algorithms. And it's a real-world task with an inherent time dimension, and you can just generate an unlimited amount of data. Now, the important thing, what is your future contribution? I'm looking forward to see next year. Those are novel SNN-based receivers improving the optical communication, so a lower BR, or a neuromorphic receiver for energy efficient communication, so that a network provider say, hey, we want to have your SNN inside our receiver. And with that, thank you for your attention.